Welcome to the next problem solving session, week 8 of Fundamentals of Food Process Engineering. So, we'll be discussing some problems as well as some theoretical questions. And if you guys have any doubts or answers to these questions, you can post it in the messages, or you can unmute yourself and answer the question. So, first question, match the following: A sorter diameter, B Stokes diameter, C surface diameter, and D volume mean diameter. The other side we have having the same surface area as that of the particle, having the same surface to volume ratio of that of the particle. Third, the mean diameter D is equal to summation of x1 d1, where x is your weight fraction and D is the diameter of that particular weight fraction, and falling at the same terminal velocity. So, do any of you know what these terms mean? Sorter diameter, Stokes diameter, surface, and volume mean diameter. So if you guys know the answers also, you can message in the group chat. Okay, so the first sorter diameter, it's like when you're doing a size reduction process, your particles or your food particles may not be of a regular shape. It won't be spherical, but it will be very irregular shape. So for that, determining the diameter of an irregular shape becomes very difficult. So what we do instead is we have um, we measure certain kinds of diameters of an equivalent sphere. So if your particle has a certain surface area or or a volume or so, we will find out the diameter of a sphere that has the same surface area or same volume or same surface to volume ratio. So depending on what we are keeping same, our diameter names will also change. That is, the definition of the diameter will also change. So for example, sorter diameter is also known as surface volume mean diameter, which means that it is the diameter of a sphere with the same surface to volume ratio as that of the particle. So your particle will be irregular in shape, and whatever surface to volume ratio that particle has, the same surface to volume ratio the sphere will also have. So the diameter of that particular sphere is known as the sorter diameter. So A is actually A corresponds to 2, that is having the same surface to volume ratio of the particle. So the formula for sorter diameter, that is given by DSV, is equal to summation of n1 d1 cube, where n1 is the number of particles of that particular size, d1 cube is the diameter of the particles of that particular size. So when you're doing a size reduction, not all the particles will be of the same diameter. You will have a range of distribution of diameters, and so across the range you need to find out one single mean diameter, and that diameter can be either sorter diameter, Stokes diameter, surface diameter, and so on. So for sorter diameter, for across the distribution of particles that we have, we can find out the mean sorter diameter by this formula. That is sigma n1 d1 cube, where n1 is the number of molecules, d1 is the diameter of that particular range, divided by n1 d1 square. And when you convert number of particles into weight fraction, this is what you get, 1 by sigma x1 by d1. So all these formulas are given in the lecture, I think lecture 37. You can go back to those lectures to find out more about these concepts. So sorter diameter is the diameter of a sphere with the same surface to volume ratio. Moving on to Stokes diameter. Stokes diameter is the diameter of a sphere that has the same terminal velocity as that of the particle. So when you have, say, a kind of an emulsion or so, where you have one particle dispersed in another medium or another particle, so that will have a certain settling velocity or a terminal velocity. That is, the dispersed phase will have a certain terminal velocity or settling velocity in the other fluid. So the diameter of a sphere that has the same terminal velocity as that of the particle is called the Stokes diameter. And surface diameter is also known as the number surface diameter. For surface diameter, diameter of the sphere that has the same surface area as that of the particle. So you had your sorter diameter, which is surface to volume ratio. This has the same surface area. So surface diameter is also known as number surface diameter, and it can be given by this formula. ds is equal to root of n1 d1 square by n1. Again, n1 stands for number of particles, d stands for the diameter of that particular range of that particular number of particles. And when you convert your n into x, that is from number into weight fraction, this is the formula that you get, x1 by d1 divided by summation of x1 by d1 cube. And the next is volume mean diameter. Volume mean diameter or volume moment weight moment diameter is the diameter of a sphere that has the same volume as that of the particle. So dV is equal to n1 d1 4 by n1 d1 cube, which equals to, when converted to a weight fraction, will give you x1 d1. So the answer to this question is option C. So if you look at match the following, Sauter diameter is the one that has same surface to volume ratio. Stokes diameter has the same terminal velocity. Surface diameter has the same surface area, and volume mean diameter will have the same volume as that of the particle and can be given by d is equal to summation of x1 d1. So since these are a lot of formulas, there is actually a generalized formula to find out the relation between your diameter and your diameter of each and every particle and the number. So you can actually give a generalized formula as d q comma p is equal to sigma d per qn divided by sigma d per pn, where d is the diameter again, n is the number of particles. So according to what diameter you are going to find out, your p and q will vary. So for number, your p and q will be 0, for length it will be 1, for surface it will be 2, for volume 3 and moment 4. So in order to explain this better, let's say we want a number length diameter. That is, it has the same dimensions, that is the linear dimension as that of the particle. So in this case, number will be 0, this will be p, this will be q. So number p equal to 0, length will be q, which is equal to 1. So when you substitute p and q in this formula, you will directly get the relation between number length diameter and the diameter of different particles and its number as well. So in case of surface volume diameter, which is the Sauter's diameter, surface will be p, the second will be q. So surface is 2, volume is 3. So p is 2, q is 3. So when you substitute here, you will get d cube n divided by d square n, which is the same formula that we saw in the previous slide. Same for number surface diameter, which is nothing but your surface diameter as mentioned in the previous slide. Number will be, that is p will be equal to 0. Surface, that is q, will be equal to 2. So again, when you substitute here, you will have d square n divided by d power 0 n. So this is more of a generalized formula that will help you to understand instead of memorizing the formulas. So more about this is given in Introduction to Food Process Engineering by P.G. Smith. If you want, you guys can go refer to that. So any doubts so far? What are the different kinds of diameters? There are more actually, but I have here discussed only 4 of them. Any doubts so far? Why we have something called an equivalent sphere? Okay, if you guys want me to repeat something, you can let me know. Moving on to question 2. Statement 1. According to Rittinger's law, the energy required to reduce a particle size is proportional to the linear dimension of the particle. Statement 2. Rittinger's law is more accurate for fine graining. So what do you think? Which of these are true and which of these are false? Any idea? So any clue what is Rittinger's law and why is it used? Okay, so since when you try to break down particles, obviously you need to give some energy. So the energy required can be proportional to different, according to different laws, the energy required can be proportional to different characteristics of the particle. So according to, so let's say this is the generalized formula, that is the energy change dE required for size reduction of a particle by a small change dx. So let's say the particle undergoes a small change in size, that is dx, and the energy required to bring about this change is dE. So dE by dx is given by minus C x power minus m. So you have a minus here because greater the change you need to give. So that is a small x is the dimension of the product. So the more smaller you want the dimension, the more larger you need to give the energy. That is why it is inversely proportional. So x is not the change here, the dx is the change. X is actually the dimension. So the smaller the dimension you want of the product, that is more fine product you want, more energy you need to give to break down the product. So you have an inverse proportion here. So dE by dx is equal to minus C x power minus m. So this is a very generalized formula. Using this, there are multiple laws that were proposed, and there are three different laws that we'll be discussing in this chapter. First is the Rittinger's law. So the Rittinger's law assumes that the energy required is proportional to the surface area of the particle. So since x is the linear dimension, x square will give you the surface of the particle. So m is equal to 2. So since surface area is one linear dimension into another linear dimension, we will have m is equal to 2 here. Hence, energy required is not proportional to linear dimension. Energy required is proportional to the surface area. So m is equal to 2. Hence, statement 1 is false. Is this clear? This is Rittinger's law. There are other laws that assume that the energy required is proportional to different other characteristics of the particle. But for Rittinger's law, it is the surface area that is proportional to the energy. So dE by dx is equal to minus Cx, where m is equal to, so you substitute m is equal to 2, we get x power minus 2. So when we integrate this from 0 to E being the total amount of energy required, and we integrate this dimension from xf to xp, where xf is your dimension of your feed, that is the inlet feed. XP is the dimension of your product, that is after grinding, after crushing, whatever is the dimension of your product is XP. So from 0 to E and XF to XP we are integrating, and upon integration we get E is equal to KR into 1 by XP minus 1 by XF, where KR stands for Rittinger's constant. And Rittinger's law is an empirical model and was found to be much more accurate in predicting the energy required in case of fine grinding. That is, if you want your product to be very, very finely ground or very, very finely reduced to a size, that is when you will use Rittinger's law. Otherwise, Rittinger's law is not very accurate and hence cannot be applied. So hence, statement 2 is true. So for other coarse grinding and other intermediate grinding, we have other laws that we'll be discussing soon. So for Rittinger's law, it is only applicable for fine grinding. So the answer to this question is option A, that is statement 1 is false. It is dependent on the surface area, and statement 2 is true, that is it is used for fine grinding. Is this clear? Anything needs to be repeated? Okay. So moving on to the next question. Which of the following statements are incorrect? Bond's law is used for intermediate grinding. According to Bond's law, energy is directly proportional to the size reduction ratio. Kick's law is for coarse grinding and assumes m is equal to 1. Rittinger's law is for fine grinding and assumes m is equal to 2. So have you heard of Kick's law and Bond's law now that we have discussed Rittinger's law? So this is, as I mentioned, this is the generalized formula, that is any change in energy required, dE divided by dx, that is any change in the size, is equal to minus C x power minus m. So Rittinger's law, as we saw, the energy is proportional to surface area. So m will be 2 here, that is x square is what you are looking for. That is Rittinger's law and is applicable for fine grinding. So for other types of grinding, other laws were developed. The second law was Kick's law, and this was applicable for coarse grinding. So Kick's law assumes that your energy is proportional to the linear dimension, that is the length of your particle or the diameter of your particle. So energy will be proportional to the linear dimension. This linear dimension is also known as the size reduction ratio. That is, you are looking at the diameter or the radius or the length of the particle. So energy is proportional to the linear dimension. Hence, m here will be equal to 1. That is, you are looking only at x and not x square. And Bond's law is applicable for intermediate grinding. And here, energy is proportional to the square root of surface volume ratio. So, in this case, m is equal to 3 by 2. So, hence, as you can see here, Bond's law is used for intermediate grinding. Hicks law is used for coarse grinding and assumes m is equal to 1. That is for linear dimension. Rittinger's law is for fine grinding and assumes it is proportional to the surface area. But Bond's law, energy is directly proportional to the square root of surface volume ratio and not size reduction ratio. So B is incorrect. The answer to this question is option B. So these are the three laws that have been discussed in the lectures, and the problems are also related to these three laws as well. So any doubt regarding these three laws? So according to what kind of grinding we are looking at, we will apply different laws here. So moving on to question 4. Which of the following is commonly used for extraction of sugarcane juice? A. Serrated crushing rolls, B. Jaw crusher, C. Gyratory crusher, and D. Hammer mill. So ever heard of any of these four kinds of size reduction equipments? So for serrated crushing rolls, what happens is you have two long cylinders or rolls, and since it is serrated, it means that the surface of these rolls are not smooth. They are jagged. They either have spikes or they have some ridges or so, and both these cylinders will be moving in opposite direction and at different speeds. So while it is moving in opposite direction at different speeds, you have a small opening between the two cylinders where you'll feed in your inlet food product, and because of the two rotatory motion of the cylinders and the serrated surface, the particle size will be reduced and hence you will get a product down. This is serrated crushing rolls. And if you have ever seen sugarcane juice stall somewhere in the roads, you can actually see that the machines are made up of these serrated crushing rolls which move in opposite direction as you insert the sugarcane stick inside it. So the food is placed between the two rolls and the size is reduced as a result of compression, impact and shear. So the rest of the, I'll just explain briefly what the rest of the crushers are. So in case of a jaw crusher, you have a V-shaped mechanism where one of the jaw is stationary, the other jaw can be movable. So you will have this jaw moving from this direction to this direction, and as it moves, it kind of hits against the, it kind of compresses or crushes the inlet feed, and then you get a fine product down below. So as it crushes, as it hits the stationary jaw, your product is getting crushed and the size of the product is reduced. So this is a jaw crusher. In case of a gyratory crusher, you have a funnel-like casing, and you have a conical head kind of mechanism. And this conical head will keep on rotating and shaking continuously. And because of this rotating and shaking mechanism, as and when your food goes down, because of this shaking, it starts crushing the food, and your fine food product is released through the gap between your head and your casing. So this is what is gyratory crusher. And according to the RPM of this gyratory crusher and as this moving jaw, you can get different sizes of your food particle. And in case of a hammer mill, you will have more of a hammer inside your equipment, and as your food product goes inside, the hammer will provide an impact against your food that will crush the food particles, and below you will have kind of a sieve or a screen. So only those particles that are smaller than that screen can come out, whereas those particles that are still bigger will still continuously be crushed by the hammer till it comes to your desired size of the particle. So these are the four kinds of equipments that are discussed here, and sugarcane juice is actually extracted by these serrated crushing rolls. So the answer to this question is option A. So can anybody tell me the difference between compression, impact and shear? So you have, yeah, please.
Uh, in compression, generally the volume reduction happens.
Yeah, sure. But since we're talking about size reduction, that will happen even if you keep impact or shear. At least in this particular process that we're handling, size reduction will obviously result in a volume reduction as well. But the mechanisms are different: compression, impact, and shear. So how do these mechanisms differ? So in case of a compression, yeah, volume will be reduced. But in case of compression, you are acting force on both the directions. So it's the very first chapter itself. We kind of explained about the tensile force and compressive force acting in a unidirectional manner. So compression will basically give force on all the on two sides of the product to reduce the size and as well as the volume of the product. So this is compression. Impact is you're actually throwing or you're directing the food product towards a stationary metal or a stationary jaw or something like that, so that because of that impact, that is the force in which it hits the metal, stationary metal, because of that force the product will crack and will become of a smaller size. That is impact. And in case of a shear, you will have more of a tangential force. Well, like say attrition or so. Attrition is kind of a mechanism where you kind of have plates that are rubbing against each other. Because of that rubbing against each other, the food product between the plates will undergo friction. Because of that rubbing, they will undergo friction, and that friction will result in a volume reduction or a size reduction. So the way in which the force is acting is different for all of these three cases. Compression is more of a unidirectional force. Impact is where your food is getting impacted onto a stationary object. And shear is where it is placed between two plates and you give a tangential force or a frictional force. And that frictional force will result in breakage of the product. So moving on to question 5. Any doubts in these three mechanisms? So you can actually get nice diagrams in Google if you try to find out what is the difference between compression, attrition, and uh, impact as well. So moving on to question 5. A cylindrical shaped food material has a length and diameter of 12 millimeter and 8 millimeter respectively. Calculate the equivalent surface diameter. So do you remember what is the surface diameter? What is the definition of a surface diameter? We discussed this in the first slide. So surface diameter, that is since your particles are irregular, you need to compare it with a sphere of a diameter that has the same surface area as that of the particle. So equivalent surface diameter is the diameter of a sphere having the same surface area as that of the particle. So can you now figure out how to find the equivalent surface diameter? What is the logic behind this question? How to go forward?
We calculate the surface area,
Hmm.
and from the surface area we can have the surface area formula for the sphere.
Yeah.
From that we can calculate.
Yeah. So what is the surface area of the cylinder that you are getting? Can you calculate? So when you substitute the values of R and H, R as 4 millimeters and H as 12 millimeters, the surface area of the cylinder that we will be getting is 2 pi into 4 into 4 plus 12, which is 401.92 millimeters square. In case you guys are calculating, I'll slow down or else I can move on to the next step. You can let me know if you want to move to the next step. So from this, what is the diameter of the sphere that you are getting? Equivalent surface diameter. Okay, so since the surface area of the sphere is equal to the surface area of the particle, for a sphere the surface area is pi d square. That we equated to the surface area of the cylinder that we just calculated. So from this you are getting d as 11.31 millimeter. The answer to this question is option D. I hope this is clear. So moving on to the next question. The same dimensions, the cylindrical shaped food material has a length and diameter of 12 millimeter and 8 millimeter. Calculate the sphericity of the particle. So when you mean sphericity, it actually means since your particle is irregular in shape, sphericity will give you an idea of how close it is to a sphere. So any clue how to calculate sphericity? So sphericity of a particle can be given as surface area of a sphere having the same volume as that of the particle divided by surface area of the particle. So the more and more these are same, the more you can say that the particle is very close to being a sphere. So from the previous question itself, since the dimensions of the particle are same, we calculated 2 pi r plus h, that is the surface area of the particle, as 401.92 millimeter square. So what is the volume of the particle that you guys are getting? So volume of the particle can be given as pi r square h. When you substitute the values, you get pi into 4 square into 12, which is 602.88 millimeter cube. So here it is the surface area of the sphere having the same volume as that of the particle. So now you will equate the volume of the particle to that of the sphere. From there you will calculate the diameter and then the surface area of the sphere. So pi by 6 d cube, which is the volume of the sphere, is the same as volume of the particle. From this you can get d. So what is the value of d that you are getting? So the d value that we get is comes close to 10.5 millimeter. So the surface area of the sphere is pi d square, which is pi into 10.5 square. So you're getting the surface area of the sphere as 346.19 millimeter square. So now you have the surface area of the sphere and you have the surface area of the particle. So the surface area of the sphere divided by surface area of the particle will give you sphericity, which comes out to be 0.86. And the more and more this is closer to 1, the more it can replicate a spherical particle. So the answer to this question is option A. So moving on to question 7. If you guys have any doubts, you can just stop me there and ask. Question 7. A material is milled from 15 millimeter to 2.5 millimeter using an 8 kilowatt motor. So what size motor will be required to reduce the size to 0.2 millimeter using Kick's law? So Kick's law, what is the assumption of Kick's law as we discussed in the second slide? So in Kick's law, it assumes that your energy is directly proportional to the linear dimension, that is the diameter or the direct length of your product. So in that case, you will assume m is equal to 1, and when you actually integrate, this is the formula that you get. E is equal to kk, which is your Kick's constant, into natural log of xf by xp, where xf is the dimension of your feed, xp is the dimension of your product. So from this you can calculate the energy required for a product to be milled using Kick's law. So here we have the energy, which is 8 kilowatt. We have XF, which is your size of your feed. We have XP, the first one of the product, which is 2.5 millimeter. And for that we have the energy as 8 kilowatt. So with that we can calculate your KK, which is still unknown here. That is, the Kick's constant is still unknown. So we calculate the Kick's constant, and from there we can calculate the energy required to reduce it to 0.2 millimeter instead. So when you substitute the values, 8 is equal to kk into ln of 15 by 2.5. So since it takes 8 kilowatt motor to reduce to 2.5, we'll substitute the values. And the value of kk that you will get, that is Kick's constant, is 4.46 kilowatt. Is this clear? If you want me to slow down also, I can slow down. So for any product, the Kick's constant remains constant for a particular product, and for a particular kind of a mechanical efficiency, your kk remains constant, which is 4.46 kilowatt. So this, when you back substitute here in the equation, now you have xf also, now you have the second xp also that you require here. So from there you can calculate the energy required. So energy is equal to kk into ln of xf by xp. So kk, that is the Kick's constant, remains the same irrespective of how small you want the product to be. So 4.46 ln of 15 by 0.2, that is xf by xp. From this, E is equal to 19.3 kilowatt. So the answer to this question is option C. So similarly, if given for your other Rittinger's law also, you can find out through this. Any other doubts? So moving on to question 8. The work index of a material is 5.85. If 80% of the feed and 80% of the product can pass through a sieve opening of 3500 micrometer and 450 micrometer respectively, the power consumed to crush 120 kg per hour of sorghum is the following. So we'll first find out what each of these terms mean. So the moment you find out the word work index, it means it is it actually falls under Bond's law. Bond's law is what works with work index. So I'll briefly explain what Bond's law is. So Bond's law assumes that energy is directly proportional to the square root of surface to volume ratio. So your m will be equal to 3 by 2. 2 by 3, sorry. Yeah. So in that case, E will, when you integrate the common equation, you will get E is equal to power divided by m, which is your mass flow rate, is equal to 2 into kb into 1 by root of xp minus 1 by root of xf. This is what you will get after integrating the common equation that we discussed in slide 2. So here again, xp and xf are the sizes of your product and feed. So the minimum size that is required to consider here is 80%. So when you have, like, say a product that has 80% of, say, 2 micromolar, 2 micrometer, and the rest 20% are in somewhere around 10 micrometer, you will actually consider the size of the product as 2 micrometer only. So if 80% of the product is at a certain dimension, you can assume XP to be that dimension. So in this case, 80% of the feed is 3500 micrometer. So you can actually assume that XF is 3500 micrometer and XP 80% of the product is 450 micrometer. So you can assume XP as 450 micrometer. So the minimum percentage required is 80% in this for this formula. So so the relation between work index and your Bond's law is that first we need to find out what work index is. So work index is the energy required to reduce unit mass of a material from infinite size to a size where 80% of the material is below 100 micrometer. So the work index is only using Bond's law. It is not using Kick's law or Rittinger's law. So the moment you find work index in a question, you can assume that it is Bond's law and continue. So, as I mentioned, work index is the energy required to reduce unit mass from infinite size. That is, XF will be infinite and your 80% of the product material will be 100 micrometer. So, XP will be 100 micrometer. So, when you substitute those in the equation, so energy required will be Wi now is equal to 2 kb into 1 by root of 0.1. So, in this, XF and XP should be in millimeters, not micrometers. That is how you will substitute in the formula. So to convert 100 micrometer into millimeter, that will be equal to 0.1 millimeter. So root of 0.1 minus 1 by infinity, because you are reducing from an infinite size of a field to 100 micrometer, which is 0.1 here. So hence 2 kb is equal to, since this goes to 0, 2 kb is equal to root of 0.1 into Wi. So 2 kb is equal to 0.316 Wi. So now you can substitute back, since you don't have kb here in the question, you have only work index. You can substitute this back in the equation to find out what is the power required. So now your energy will be equal to power by mass flow rate is equal to 0.3162 into work index into 1 by root xp minus 1 by root xf. So any doubt in this derivation? So XP and XF will be in millimeters range. Power will be in kilowatt. M will be in ton per hour. Since it's an empirical model, this is how you would have to use it. So when you substitute the values, we want the power required here. We don't want the energy required. So the power is equal to M into 0.3162 into Wi into 1 by root of XP minus 1 by root of XF. So mass flow rate is given as 120 kg per hour. Since this formula requires only in tons per hour, you will divide it by 1000. So converting kg per hour into tons per hour will be 120 divided by 1000, which is 0.12 tons per hour into 0.3162 into Wi is given as 5.85 in the question. And XP is given as 450 micrometer. So we need to convert it into millimeters. So that will be equal to 0.45. And XF is 3500 micrometer. So again you will convert it into millimeters, which is 3.5. So note that power is in kilowatt, M is in tons per hour, your XP and XF will be in millimeters. That is when you will get power in kilowatts. So when you substitute these values and find out the answer, power is 0.21 kilowatt. So a very similar question is also there in the current assignment, where instead of work index, they'll give you the total Bond's energy constant itself. So from there you can calculate what is the power required. So the answer to this question is option D. Any doubt on how to derive the formula or how these equations came? Moving on to question 9. Calculate the fineness modulus given this is the following particle size analysis. So as I mentioned, in a product or a feed, all the particles will not be of the same size. You will have a distribution here, and because of the distribution, each particle will be of a different diameter. So how a particle size analysis is done is that you will have a stack of sieves. Sieves is a tray with perforation of a particular size. So you'll have a stack of different sieves and you'll have a pan at the bottom. So when you pour your feed into the top sieve and you start shaking the sieve, according to the size of the product, if your product is smaller than the sieve size, it will come down. If it is larger than the sieve size, it will be retained. So, and in the stack, each stack will have a different size sieve. That is, your first sieve will be of say 100 micrometer diameter. Each perforation is 100 micrometer diameter. Your next will have 50 micrometer. Next will have 30 micrometer. Next will have 15. So as you can see, the size of your holes in that sieve will keep on reducing, and as you pour your feed on top and you keep shaking the sieve, like products that are higher than 100 micrometer will be retained, whereas product that is lower than 100 micrometer will go on to the next sieve. So again, products that are higher than 50 micrometer will remain, product lesser than 50 will go on to the next sieve. So like that, when you keep shaking, you will have some in the pan, some retained in each of the sieve according to its size. After that, you need to take out each sieve and calculate how much is the weight of the product retained. So this is how you will calculate the particle size analysis in a feed or any product stream as such. So here you have different sieves, that is, it starts from 100, then you have a lower 50, then 30, then 15, and then you have a pan where you collect your fine product. So when they measured the product at each and every sieve, you have 10 grams at 100 at the 100 micrometer sieve. Then you have your 18 at 50. You have 26 grams in 30, then 34 in 15, and finally in the pan you have 12 grams remaining. So from this, when you have a certain food product with different size particles, you need to figure out how fine the particle is. So fineness modulus will help you calculate how finely the particle is being reduced. The fineness modulus is an empirical number obtained by the summation of fraction of weight retained in each of the sieve multiplied by the sieve stage. So I'll explain how to calculate the fineness modulus. So what fineness modulus gives is that it will give you an idea of how coarse or how fine the product is after the size reduction. So lesser the value, more fine the product is, higher the value, more coarse the product is. So fineness modulus will give you an idea of how the characteristics of that product is. So in order to calculate the fineness modulus, as mentioned here, you need to sum the fraction of weight retained in each of the sieve multiplied by the sieve stage. So how to calculate this is that, first, since you have, this is the sieve number that was given in the question. So a stage is starting from the bottom, that is, your pan will be considered as stage 0, that is where you collect your product. Then as you go up, your stages will increase. This is the first stage, that is 15 is the first stage, 30 is the second, 50 is the third, 100 is the fourth. So this is how you will mark the stages of your size analysis equipment. So pan starts with 0 and your first C will be a highest stage. So the weight retained is given in the question. So you need to calculate the total amount of product that you sent in. Here we don't consider any loss in the product at all. Whatever you feed in is what is going to come out at the other end or will be retained. So the total amount of product that you fed in is the sum of all the weights retained at each and every stage. So if you sum all the product that is retained in each and every stage, you will get the total amount of feed that you sent in. So if you add 10 plus 18 plus 36 plus 34 plus 12, you will get 110 grams. So this means that 110 grams is the amount of feed that you sent inside the equipment. So this will be a total. So the fraction of weight retained is the amount of weight retained in that sieve divided by the total amount of weight that you sent in. So this is what is fraction retained means. So for this stage 4, the fraction retained is 10 divided by 110. For stage 3, it is 18 divided by 110. Stage 2, 36 divided by 110. Stage 1, 34 divided by 110. Your pan is 12 divided by 110. So these are the fraction of weight retained. But we found out that fineness modulus is sieve stage into the fraction of weight. So you need to multiply the stage into the fraction of weight. So in this case, 4 into 10 divided by 110 will give you the fraction of weight retained into sieve stage. Again, 3 into 18 divided by 110 is the fraction into sieve stage. 2 into 36 divided by 110, which is 0.65. 1 into 34 divided by 110, 0.30. And 0 into 12 divided by 110 is 0. So these are the fraction of weight retained into the sieve stage. So the summation of this will give you the fineness modulus. So when you sum 0.36 plus 0.49 plus 0.65 plus 0.30, you will get the value as 1.81. So the fineness modulus is 1.81. The more lesser the value, more fine the material is. So any doubts on how to calculate the fineness modulus, how to calculate the stage, how to calculate the fraction of weight retained? In case you want me to repeat any step, I can repeat it again. So the answer to this question is option D. Moving on to the last question. The critical speed in a tumbling mill is A. The minimum speed required to reduce the size of the particle to a desired value. B. The speed required to reduce the size of a particle by half. C. The speed required to reduce the size of a particle by tenfold. And D. The speed at which the centrifugation process is observed. So any clue what the answer is and what a tumbling mill is?
So ball will be placed inside the rolling cylinder. That's
Yeah.
the
Yes, so your grinding medium will actually be the balls inside a mill that is being continuously tumbled or rotated. So what is the critical speed?
speed at the centrifugation process.
Yeah. So you'll have multiple balls which act as a grinding medium inside your tumbling mill. And as the tumbling mill is rotated, your balls will also stick to the walls. And at some point of time, your gravitational force will actually dominate and your balls will start falling. And because of this falling, your fruit product is actually getting compressed, and due to compression and attrition, your food products size is getting reduced because of the impact of the balls. Your size reduction is happening. But if the speed of your tumbling mill is so high, then the gravitational force will not dominate. In fact, your centrifugal force will start dominating instead of the gravitational force, and your balls, instead of falling down, will stick to the walls and remain in that way. So since your balls are not falling down, there is no compression or attrition that is happening, and hence your size reduction will also not happen. So this is how your normal process should happen. This is what will happen if you are operating the tumbling mill at a critical speed. So the speed at which a centrifugation process is observed is known as the critical speed. So the answer to this question is option D. So that's all for today's class. In case you guys have any doubts, you can either post it in the discussion forum or you can mail me.